Okay, so one of the applications that is envisioned for the drones is, of course, the delivery. And one immediate question that you may ask yourself is, given a set of delivery centers, I have these red, blue dots on the map. So these are the possible delivery centers from which the drones would deliver. How would you split the area, in this case, the city of Norrköping and surroundings, so that in every cell of the partition, you have the same distribution center that delivers to all customers in the cell? So this, center would deliver everywhere here, this center would deliver everywhere here, and so on. So this would deliver here. So what would be the right way to split the customers into the service areas serviced by the different distribution centers? And of course, there are many questions that need to be answered before you do such a split in a good or optimal, sensible way. But for starters, we may assume that nothing matters for the customers. The centers are all the same or provide the same level of service. So it's not like we go into different shops, or I don't know, different hairdressers or other services where we care about many things except for location. It could be that with the service centers, we don't even really care from where our supply comes. So it can be something that is very common, like food items, or it could be some medical devices like the defibrillators, where indeed the customers, the last thing that they think about is from which distribution center the device is coming. All they care about is that it comes as fast as possible, comes from the closest center, or in other words, we want to split the area, our region, into the cells, so that within every cell there is one distribution center that takes care of all the customers in the cell, and the distance to this distribution center from any point in the cell is smaller than the distance to any other distribution center. Okay, so again, no matter which point in the particular cell you take, it should be closer to its distribution center than to any other distribution center. Okay, so that's the question: how to split the city or the area into such cell, and the answer is given by something called the Voronoi diagram. So Voronoi is a name of a person, and Voronoi diagram is a very widely used tool in various domains, but in particular for this understanding of where should the areas for different service centers be. And it has quite a long history, the Voronoi diagrams. You can see it in many textbooks and lectures and even in blog posts. And it has been known historically as the post office problem. So yeah, these distribution centers that I was mentioning were the post offices, and then you wanted to think how to split the area into the zip codes. So which post office should service which area? Yes, again, you can see that's about post offices. And then, well, here on the picture, you don't have the post office or any area. Here it was, so if, I don't know if you see the lines when I'm sharing it in Zoom, but hopefully you may see it in the lecture. So these are the cells into which the area, in this case, this frying pan or whatever this is, was split by the different seeds from where the dough was prepared. Anyway, that's just a fun application of Voronoi diagrams. So you plant in several places, you put in some dough, and then it starts growing and expanding. And yeah, the boundaries between the different pieces, they also form this Voronoi diagram. You'll see this picture later. Anyway, don't worry too much about this application. It's just fun. So what I was really emphasizing here at this slide is that even though historically the Voronoi diagram was known as the post office problem, because, well, every post office would want to serve the area which is closest to it. The postmen, they don't fly, or at least they didn't fly before the drones were here. And maybe for deciding the zip codes, deciding which areas should be served by the different post offices, it would have made more sense to look at the road distance rather than at this Euclidean distance, the straight line and distance between the points. So historically, yes, that's how Voronoi diagram came in, but maybe it's now when they're actually getting their real meaning and real sense. So here I'm showing the Voronoi diagrams in the so-called network metric, where the distance is not the shortest flown distance, but the distance along the roads. So again, you see some service centers or whatever these points are. But then again, the distance is measured using the road network, not using the straight flight distance. And here are some, oh, sorry, I meant to change the slide. Here are some more examples. Again, you have these schools, the red schools, and then the question is how do you split the city into the schools so that the kids travel to the schools as little as possible. Here is another picture with a Voronoi diagram by restrooms in the department store. So, in the department stores, and there could be multi-story buildings, you often see these signs, left to right, how to get to the closest restroom. Well, it's a Voronoi diagram. Every restroom has its Voronoi cell, and for every point in the cell, this restroom is the closest among all the restrooms. But again, closest not in terms of the crow fly distance. I don't know how fast people try to fly to the restrooms, but still they have to be constrained by the network of whatever the corridors, and maybe there are escalators and elevators and other things. So in this metric induced by the fastest means to travel, you have the Voronoi diagrams. But returning to our particular applications, when we are talking about drones and about the distribution centers, the drones would, or at least could, fly directly. And then the original Voronoi diagram, which really is using the Euclidean, the straight line distance, it kind of comes back because you don't really have to follow any road network or anything when your drones fly. So sometimes this Euclidean distance is called as the crow fly or as the bird fly, or maybe we could say as the drone fly distance. And yes, it's important when we're talking about deliveries by drones, but also, if you want to have some charging stations, some infrastructure for the drones, we will be talking about infrastructure in the short last lecture today. Again, depending on where the drone is, maybe the drone is here and it has to know to which charging station to fly to get charged as fast as possible. Well, if the drone is in the cell of this station, then it has to fly to this station. If it's in the cell of this station, it has to fly to this station, and so on. So here is again the Voronoi diagram for you. Now, interestingly, when we look at the multitude of drones, and this is probably what we would think about if you think about a distribution center, when the drones would fly out of it and back to it, it's really good that the drone paths would be non-crossing. So the drones that go, from this cell to its center, and the drones that go from this cell to its center, their paths are non-crossing. Each of them stays in its own cell or in its own zone, or whatever you want to call it. And moreover, if the drones just go back and forth, then the drones that go from the same distribution center, they also don't interact with each other because they go just back and forth. So of course there is some congestion and maybe there is some scheduling that needs to be applied at the distribution center. But other than that, everywhere else, the paths are non-crossing. And it does give you some ideas of the zonation of in which zones how the drones would fly. There is a hot topic that I might have mentioned in the air risk lecture. The question is whether the drones should fly along the corridors, like a predefined set of routes, or rather than there should be zones, and in different zones there should be different rules for drones and maybe different USSPs, space service providers taking care about the drones and the conflict in them. So that's a hot question. So kind of zonation versus corridors, you may see and hear it and pop up in various domains. Anyway, here there is some answer that you have these zones for the drones, and every zone is associated with a single distribution center, and the traffic is non-crossing. And just to connect it to something that we talked about earlier, well, as you may recall, also in air traffic management in general, but in particular in drone traffic management, there are two different problem settings. Of course, they're connected. You plan route for many drones, plan route for one drone, but still, there is a set of problems when you're focusing on planning a route for a single drone, or for a single, or just planning a single route. And there you have all these questions about risk and other things that we look at, versus managing many drones, as you see here on the right in the video where we have simulated flights of many drones over Norrköping. So the kind of really the crux of the UTM or what USSP, space service provider, would do is managing many drones. But when you think about a single operator, well, the operator cares about, the operator may have many drones and many missions, but every time an operator plans a route, the operator plans a single route. So that's kind of a different question. I wanted again to emphasize the difference between two different problem settings, even though they are connected. Okay, before we go into what kind of more of understanding of what the Voronoi diagram is, I want to recall what Dijkstras' algorithm for finding shortest path in graphs does. And I realize maybe not all of you have seen it. So if you see it for the first time, don't worry. That's all I wanted to show in this particular slide. And in particular, if you took the algorithms course with me, I might have shown this idea of how Dijkstra algorithm on the graph can be viewed as the wave propagation. So the setting here is that, well, we have this node S, from which we compute in the shortest path, and we may compute the shortest path to a single node T, or compute shortest path to all the nodes, and hence compute the shortest path tree, as we also had in the previous lecture for shortest path in polygonal domains, shortest path to all vertices of the polygonal domain. And the Dijkstra's algorithm maintains this set of reached or visited vertices, and at every iteration it expands this set by kind of propagating the wave. So at any time there is what you can call wavefront, the boundary between those vertices that have been already reached or visited by the algorithm to the shortest path to which you know, and all the other vertices. And as the algorithm progresses, the wave goes farther and farther away from S, and then it reaches the next vertex. The vertex becomes visited. You set its label, and then the wave propagation continues until all the nodes are covered. And this wave propagation paradigm, again, something that we looked at in the previous lecture for finding shortest path from a single point in a polygonal domain. It is also very much applicable to construction of the Voronoi diagram. So here you have an animation. The black dots are the sites, the service centers for which the Voronoi diagram is built. And you imagine that you have waves that start propagating from all the sites simultaneously. And the areas that are reached by the wave from a particular site faster than from another site is exactly the area, the set of points which are closer to this site than to any other site. So these areas eventually define the Voronoi cells of the sites. Okay, So this is, well, here the animation is done for the Euclidean distance. So the waves, when they propagate, they form circles before they collide. But this is true for any other metric. You can do a similar wave propagation in the network metric, the travel time metric induced by a set of roads, and then we also saw it by a metric induced by shortest path in polygonal domains, and so on. And that's also coming back to the picture with the I don't know, there's, I'll go back a few slides with this pie that somebody had in the yes, here in the blog post again. So there were these propagations from different pieces of dew that were initial in the frying pan, and as they started expanding, I know you don't see my red too much, but it doesn't matter. You can see these boundaries between the Voronoi cells of the different initial pieces. So this wave propagation shows, yes, in many domains. In particular, here we speak about wave propagation in free space. So circular waves propagate and form the cell boundaries. In particular, those places where the waves collide, we have the edges of the Voronoi diagram. So all the points on this edge, they have two nearest neighbors. So this side is as close to this point as that side. And this is true about every point on this edge, two closest sides. And where we have three wave fronts coming to a single point, like over here, for instance, we have three sides that are equidistant, or which are the nearest neighbors for this particular point. Okay, and this distance is sometimes called the Voronoi radius, and this vertex of the Voronoi diagram is called the Voronoi vertex, and the edges of the Voronoi diagram are called the Voronoi edges. But again, the important observation is that these edges are the places for which there are two nearest sites. So these guys, they don't care from where the goods are coming, from this warehouse or from this warehouse. And yes, we will be calling these warehouses, or the points for which the Voronoi diagram is built, sites. I'll have a single slide on terminology next. And we will assume that no three of them collinear, no four of them are co-circular, so that there are no degeneracies. And yeah, for instance, we always have only three nearest neighbors for any point, never have four. Okay, so that's about the edges and the vertices of the Voronoi diagram. Now, as usual, yes, terminology is the key, and hopefully it's not the mess. The word or the term point is, of course, overused. Here, when we're talking about the Voronoi diagram, we will be saying that a point is just any point in the plane. Okay, so this is the set of all points here in the plane. And the points for which the Voronoi diagram is considered, we will call them sites. Okay, so these points will be sites. Or in our delivery application example, the sites will be the warehouse. Okay, so points are all the points in the plane, and sites are these points for which Voronoi diagram is built. And the formal definition of the Voronoi diagram for, or sometimes it's say off or on a set of sites S, is a decomposition of the plane. Yes, we decompose the plane into cells, such that for every point in a cell, the closest site or the nearest neighbor is the same. Okay, so just to give this formal definition of something which is probably also intuitively clear and what we've been talking about in this lecture. So it's a decomposition of the plane such that the nearest neighbor among the sites is the same. Or if you want to speak in terms of the functions, then the cells are the level sets of the nearest neighbor function, where the nearest neighbor of a point, well, is essentially the closest site. So the closest site is the same for all the points in the plane. And there is a reason why we looked at such a formal definition of Voronoi diagram. And this is because we could, with these definitions, we can easily speak about the generalized Voronoi diagram, or something called weighted Voronoi diagrams. And Voronoi diagrams can be weighted either additively or multiplicatively. And I'll give you the definitions right here, and also some examples. So the weighted Voronoi diagram, or the additively weighted Voronoi diagram, is built for the set of sites where each site also has a time associated with it. And we first will look at the formal definition, and then how it is related to anything practical. So again, the cells are the level sets of the nearest neighbor function. So we're decomposing the plane into the cells, and in every cell the closest site is the same. But now the closest is not just the distance, but also plus the time particular to that site. So again, that's the definition, and you may think of it as the TS is the delay at the site S. So one way to think about it is that imagine that I'm trying to draw a set of skyscrapers, so they should be straight, and they may have different heights. And imagine that the drone ports are located on these different heights on the roofs of these skyscrapers. So before you're good, and then maybe you have to deliver, from one of the skyscrapers from the first floor to some point of the plane, and you would have to get the item on top of on the roof of the skyscraper, and then the drone flies to your point. And this time that it takes to get to skyscraper S is TS. So when you are deciding to which skyscraper to assign your point in the plane, you're not only taking into account the distance from the skyscraper to the point, but also the time it takes to get to the top floor of the skyscraper. Okay, so this is like a Voronoi diagram with a delay. Or if we were looking at the wave propagation paradigm for Voronoi diagram, then we would these wave propagations would start at different sites at different times. The larger the delay is, the later the wave propagation would start from that site. Okay, so that's the additively weighted Voronoi diagram. And in a similar way, you can define the multiplicatively weighted Voronoi diagram. Again, it's decomposition into cells with the same closest site in every cell. But this time, the closest means not just the distance, but you also dividing by the weight of the site. And you may think of it as the speed of a drone that starts from a certain site. So, you have different sites. And for a certain point, you are thinking, well, what should be my closest site? Well, in Euclidean distance, maybe this is the closest site, but maybe the drone from here flies so fast that you would really want to assign this point to this site. Okay, so that's the multiplicatively weighted Voronoi diagram. So these are the definitions, and here are some examples of additively and multiplicatively weighted Voronoi diagram. Another extension that I want to mention for the Voronoi diagram is the so-called order 2, or more generally order K Voronoi diagram. And again, is the composition of the plane into cells. But now within the cell, not only the first site is closest, but the two closest sites, not only the closest site is the same, but two closest sites are the same. Okay, so again, here are you have these numbered 1, 2, 3, and so on sites, and then you have these different cells. And for instance, in this cell, the two closest sites are number 2 and number 5. Okay, in this cell, the two closest sites are number 6 and number 8. And this kind of models the preference to go not necessarily to the closest site, but maybe to the second closest, or more generally for general K to the K closest site. Okay, so now back to the usual Voronoi diagram when we decompose them into the cells so that the closest site is the same within the cell. So remember, we realized that the cell boundaries are the places where you have more than one closest site. And in particular, what it means is that the cell boundaries are really the bisectors between the sides. So you look at these two sides and you draw the bisector between them, or the locus of points that are equidistant from the two sides. Sorry for my drawing, we'll go to GeoGebra in a second where it will be more precise. So yes, the bisector between 2 points is the perpendicular bisector line that goes perpendicular to the segment connecting the points. And the cell boundaries, they belong to these bisectors because they have to be equidistant from 2 sides. And in particular, this gives us the way to build the Voronoi cell of a site by just looking at the bisectors between the site and all the other sites and realizing what is the set of points that are closer to the site S than to any other point. And I'll illustrate it in the example in GeoGebra. So we go again to the GeoGebra Classic or whatever it is. And yeah, I'll start by removing the grid and the axis, but you don't have to do it if you work in GeoGebra. And let me just draw a few points, which would be our sites. I can move them later, so that's okay, whatever they are. Now, and I'll start building up the bisectors between, let's say, the site D and all the other sites. So here in the toolbox in GeoGebra, you have, where is it? Yeah, here. Sorry, perpendicular bisector. And yes, as GeoGebra suggests, you click on 2 points and it shows you the bisector between them. Okay, so this black line is the bisector between points A and D. In particular, if A and D were the only points, were the only sides, then everything on this side of the bisector would be the Voronoi cell of D. Everything here would be the Voronoi cell of A. Or in other words, everything here is closer to D than to A. Okay, and it's the boundary between the two is defined by the bisector. Okay, let's draw more bisectors. Bisectors between D and B. And again, everything here is closer to D than to B. Everything here is closer to B than to D. And the last but not least, let's do the bisector between D and C. And here we go. Everything here at the top is closer to D than to C. Everything here is closer to C than to D. In particular, if you look at the intersection of all these half planes, the half plane where you have points closer to D than to B, closer to D than to A, and closer to D than to C. So this triangle, this is the Voronoi cell of the site D in the Voronoi diagram of the sites A, B, C, and D. So if we want, we can try to do a polygon here between these 3 points, 1, 2, 3. I think I have to still click here. So this red shaded thing is the Voronoi cell of D in the set of sites A, B, C, and D. Okay, if you have more sites, if you have another site added, let's do that. Let's add site, E. And how does the Voronoi cell changes? Well, again, we do the bisector between D and E. Well, in this case, the change is not very large, but let's move E, or maybe let's move D. Yeah, let's move it like here. Yes. So again, this polygon, which is the intersection of the half planes defined by the bisectors between D and everybody else, this is the Voronoi cell of D. That's how you build it. And now, last but not least, I wanted to show you how to export the pictures that you have in GeoGebra. So here in the menu, well, for me, it's over here, but I understand it could be in different places depending on your screen. But somewhere there is this menu, is, well, I guess as usual now, the menus are 3 dots, so these 3 lines. You have these possibilities to save or export, and in particular to share. And I may ask you to share this. Well, you have to give the name to it, Voronoi diagram of E. And yes, you can have it private or shared. And yeah, so you save it. Now that it has the name, it also gives you the link to your drawing. You can copy the link, and I will now open it in the incognito tab. So I'm not logged in, but if everything goes right, then I will see, yes, the same thing right here. So this is how you share your GeoGebra drawing. And again, yes, you can change things and so on. And it was a bit sloppy when I was putting this point. It should have been at the intersection of the bisectors, but it wasn't. And now, yes, so these two were. So I was. So this was, and this I made it. I put it in the intersection. These two I didn't. So they don't change as I move the points. But anyway, that's not the point. What I'm showing here is the way how you can export, how you can share your GeoGebra files, and I may ask you to share on the exam or elsewhere. There is also, well, there are many other ways to export the image, but I do ask you to export image in practice exam, and we'll ask to do it in the actual exam. So share and export. And exporting, you can just do a screenshot, but you can also export it. Well, you can download a copy to clipboard and paste it into your email with answers and so on. So there are quite a few possibilities of exporting things in GeoGebra.